Alright, well, you've already seen how to simplify square roots, but we're going to talk a little bit more about irrationals and rationals. Uh, let's first mention that rational things, rational numbers, are those that can be written as a fraction. So rational things are like the number 3, because that can be written as a fraction, 3 over 1. It's still equal to 3, but I can write it as a ratio of two integers. Negative 5. That can be written as negative 5 over 1, so it's a fraction, so it's rational. 0.4, that's read 4/10, so it can be written as a fraction, 4/10, which reduces to 2/5, which is still equal to 0.4. But again, it's 0.4 can be written as a fraction, therefore it's rational. And in fact, any decimal value, as long as it has it's finite, like this 0.4 is, or it repeats itself. For example, 0.6 repeating is 2/3, and as long as it repeats itself, it can be written as a fraction, and it's rational. Irrational numbers are ones that are not fractions. Okay, and the classic example for this is the number pi. Pi is this decimal, but this decimal has no spot where you can put a repeat symbol. It's just a random string of numbers, just about. No repeating area or section at all. So it's irrational. It cannot be written as a fraction. And then it turns out things like the square root of 2, square root of 3, any root that is not a perfect square root is also irrational. So square root of 2, the only way to represent it is to actually write square root of 2. Any decimal you put would be an approximation. It's a decimal that goes on, but no repeating symbol can ever be used to write it. Same with root 3 and root 5. Okay, things like root 4 are rational because you can square root it and get a 2, which is 2 over 1. So if it's a perfect square, then it's rational. Anything that is not a perfect square is irrational. So even like 2 root 2 or 5 root 7, anything that you have to use that square root symbol to write it is an irrational number. And so sometimes when we simplify our radicals, we just have to leave it with a radical in it. So for example, square root of 50. Again, we want to look for the perfect square inside that, so it's 25 times 2, which I like to think of as a 5 squared times 2. And there is the square root of something that's squared, so that is just a 5. The 2 inside is irrational, so we just leave it as 5 root 2. Another example, 4 root 20. This 4 on the outside of the radical means 4 times the square root of 20. So we break down 20 as a 4 times 5. Square root of 4 is 2, so a 2 is on the outside now, and we multiply with the 4 that was already out there. 8 root 5 for our final answer. Let's do one that's really complicated now. Let's do negative 6 square root 32p squared q to the 10th r to the 4th. Remember, we're doing square roots, so we want things that are squared, because they are perfect roots then. 32 I'll write as 16 times 2. P squared, perfect square. Q to the 10th, Q to the 5th squared. And R to the 4th, R squared, squared. And again, these are what I'm looking for. Perfect square, perfect square, perfect square. Even 16 is a 4 squared, a perfect square. And so I can square root those. And here's what I've got. On the outside I got my negative 6 already. It's going to be times everything I take out. So I'm bringing out a 4 because the 4 is a perfect square. A p because p is a perfect square. A q to the 5th because q to the 5th was squared. And an r squared. And I'm left inside with just a 2, it looks like. And so my final answer would be negative 24. When I multiply them, p q to the 5th r squared root 2. In the last section we talked about when to use absolute values. Q to the 5th squared is guaranteed to be positive, and it's q to the fifth on the outside, so I got to put that in absolute values. P to the second power is guaranteed to be positive, but I got an odd degree on the outside, so I might just put them both in the same absolute value. That P and the q to the fifth should both be in the absolute value, giving us the best final answer. And one final one, let's do negative 13 square root of 30a7y squared. As I try to factor the stuff on the inside into perfect squares, 30 is 3 times 10. In fact, here's the complete factorization of 30. 3 times 2 times 5. None of those are perfect squares. That's fine. They just all stay in the radical. A to the 7th I'm going to write as an a cubed squared. That gives me an a to the 6th, but I had 7 of them in there, so I'm going to have an extra a tacked on. And I write it that way because I want a perfect square. And then y squared is a perfect square. So I bring stuff out that's perfect. Okay, a cubed squared, that's a perfect square. Y squared, perfect square. And what I have left inside is my 30, 3 times 2 times 5, and that extra a. Let's check to see if we need absolute values at all. The y squared is definitely positive, because it's going to, whether y is negative or positive, when you square it, it's positive. So I've got to have that guy in parentheses. A cubed, or a to the 7th rather, could go either way. So we just leave it as a cubed on the outside. We don't need absolute values around it. And so there's my final answer. Hope that helps with the irrational simplification of radicals.